Because MALDI is a pulsed technique and you have all the ions produced at the same time, it's very commonly coupled with time of flight mass analyzer. Okay, so now we're looking at ways to separate the ions. Because the time of flight works, as the name suggests, based on the time of flight, if you have ions that all have got the same energy, okay, so they've all got the same half mv squared, then ions with a higher mass are going to have a smaller velocity, and with a smaller mass are going to have a higher velocity. And so if you measure the time it takes them to travel a known distance, which is known as the drift tube, you can calculate what the mass to charge was of the ions. In order to be able to do that, you need all the ions going into the mass analyzer at the same time. Okay? Any more expecting? Okay, so we're just going over the time of flight mass analyzer. So because MALDI is a pulse technique, because the ions are all produced at exactly the same instant, so they're all accelerated at the same time, so they go into the drift tube with the same kinetic energy, they're all there together. Okay, and that's why MALDI and time of flight are usually coupled together. So for the people who've just come in, one of the important things that I've just been saying is that electrospray, because it uses a continuous flow of solvent which contains the analytes, it couples well with liquid chromatography. Okay? So you would couple electrospray with liquid chromatography, you wouldn't couple MALDI with liquid chromatography. Okay, so the time of flight mass analyzer isn't the only analyzer. There are a number of others that are used in Are we expecting any more?
Our lecture's finished, that's all.
Oh, no, I knew why you were going to be late, but I just want to make sure. Is everyone here now? Yes? So just to reiterate the important message, for those who've just come in, again, electrospray can be coupled with liquid chromatography, but MALDI cannot. And now we're talking about mass analyzers, and we just talked about the time of flight analyzer. This is another example of a mass analyzer. This is an ion trap mass spectrometer, which, as the name suggests, traps the ions. So you have these two end electrodes and this ring electrode, which is a sort of donut shape in blue. And it's just a different way of separating and sorting the ions. Okay, this type of mass analyzer has very high sensitivity, so it's used a lot in proteomics because you tend to have low abundant species. You've got small amounts of proteins, small amounts, therefore small amounts of their peptides that are generated. Okay. It can be used for tandem mass spectrometry, which is something I'm going to come on to later, but it's used very commonly in proteomics. Quadrupole is another type of mass analyzer, and this is another one which is kind of described by its name because it involves these four rods, okay, and various electric fields are applied between those rods, and the ions will form this sort of take this various trajectories through those rods. Only some of them will manage to pass through, depending on their mass to charge. Others will hit the sides, and once they hit the sides, that's it. This is a very fast mass analyzer, so if that was what you required from your experiment, you might consider using a quadrupole. They're not commonly used on their own. They're usually coupled with another type of mass analyzer, especially when we're talking about proteomics. So you'll quite often see them coupled with themselves in what you call a triple quad, or with a time of flight mass analyzer. Okay, this describes another mass analyzer, this time Fourier transform ion cyclotron resonance. This makes use of a magnet, whereas the ones we've showed so far make use of electric fields. So in the FTICR, you have a static magnetic field, and the ions will undergo cyclotron motion. So they'll go in a cyclic motion perpendicular to the direction of the magnet. And the frequency at which they cycle is related to their mass to charge. So if you can measure the frequency at which they're undergoing this motion, then you can then calculate what was their mass to charge. Okay, so if we now look at some actual mass spectra and the kind of information that we can get out when we look at them. So this is an electrospray mass spectrum of a peptide mixture, which includes the peptide LHRH. Okay, this is the sequence of the peptide. This is its elemental composition, and then based on its elemental composition, that's its mass. So if we look in the mass spectrum, where do we see it? Okay, so the singly charged species is seen here. Now remember, we have to add the proton on to get this electrically charged. We need it to be an ion, otherwise we don't detect it. And so it's seen in the mass spectrum at a mass to charge of 1182.58, okay, which is the mass of this, the neutral molecule, plus the mass of a proton. And if we focus in on this peak, this is what we actually see. Okay, so there's a number of peaks there. And the difference in mass to charge between them is 1. Okay. So this peak here corresponds to the ions where all of the carbons are carbon-12. Okay. And then the next peak along is where one of the carbons is carbon-13. Okay, so it's an isotopic peak. This peak here corresponds to those species where you've got 2 carbon-13s, okay, and 3 carbon-13s, and this one you can just see as 4 carbon-13s. Okay. So the difference in mass between carbon-12 and carbon-13 is 1. Okay. And so if we're looking at a singly charged species, then the distance on the mass spectrum between the carbon-12 isotope and the carbon-13 isotope is going to be 1, okay? Because the mass difference is 1 and the charge is 1. Okay. If we then look at this peak here, which is the doubly charged peak, so that's the peak where we've got this mass plus 2 protons. Okay. That appears at 591. So now the difference in mass between the carbon-12 and the carbon-13 isotope is going to be a half, because the mass difference is still 1, okay, it's still 1 between carbon-12 and carbon-13, but now the charge is 2. Okay, this is a doubly charged species, so the distance between these on the mass to charge scale is going to be 1/2. And that's very useful information because it allows you, if you don't know what you're looking at, you can calculate what is the mass of the peptide. So, because you can work backwards, okay. So if we look at the spacing between the isotope peaks, we know what the charge is. Because if the spacing is 1, then the charge is 1. If the spacing is 1/2, then the charge is 2. If the spacing is 1/3, then the charge is 3. Okay. So we know that this is a doubly charged species. So we want to work back towards the mass of the neutral molecule. Then we need to multiply the mass to charge by 2, okay, because we know the charge is 2. So if we want to work out what the mass is, we've got to multiply it by 2. And then we need to subtract the mass of the 2 protons. Okay, so that's it calculated for this particular species, okay? So it appears at a mass to charge of 591.79. We know that's doubly charged because of the spacing. So we need to multiply it by 2 and then take away the mass of those 2 protons. Okay, and if we follow that through, that gives us 118.51. 0.58.